Hi, welcome to this week's Crunch seminar. Today we have two speakers. For the first talk, Dr. Dibakar Datta would be presenting his work on generative AI for discovering novel materials for next generation biomedical, quantum, and energy storage applications. Dr. Datta is an associate professor in the Department of Mechanical and Industrial Engineering at the New Jersey Institute of Technology. He earned his PhD in 2015 from Brown University, where he specialized in solid mechanics with minors in physics and chemistry. His current research focuses on applying generative AI to discover novel materials for next generation energy, quantum, and biomedical applications. His research on energy storage has received international media coverage, and he is a recipient of the National Science Foundation NSF Career Award. With this brief introduction, I invite Dr. Datta to present his work.
Thank you so much. Thank you so much, Professor Kanyadakis, for this wonderful opportunity. So as I'm speaking at Brown is very special because I did my PhD here. So title of my talk is Generative AI for Discovering Novel Materials. So the overview of the talk. So I'll talk about this energy material is very detailed. So most of this talk will be focused on energy material. But at the end of this talk, I'll briefly talk about our recent work on quantum material and biological material. This is very briefly. So let's talk about energy material. So just like if we use ChatGPT and we give some question and we get answer. But if you ask ChatGPT, can you tell me a material so that I can make my battery which will last for 1 month? ChatGPT cannot give you the answer because it is not trained for it, right? So can you develop ChatGPT type framework for energy material? So we'll discuss why generative AI for energy storage, why energy storage, why and how we can implement generative AI for energy storage, then result in discussion. Okay. So energy material is very complicated. Okay, let's focus on energy material. Even Donald Trump, our president, told this.
Making batteries are very complicated. It's not an easy thing and very dangerous. A lot of explosions, a lot of problems.
Okay, so even Trump said that making batteries is very complicated. Okay? So, and batteries everywhere. Okay, so from our everyday laptop to car, whether you take anything, batteries everywhere. And energy resource is very, very important. So if you see this graph from United Nations, currently our world population is like, let's say 7 billion, but our energy consumption still manageable. We are still at 400 QBTU per year. But at the end of this century, the energy consumption will be like 3-4 times more than what we have. Okay, and population will be a lot more. So research on energy is very important. So when we talk about the battery, let's take a brief review. What exactly battery? Okay. So let's consider this is the Tesla car. So if I take off this
Let's
Tesla
explore
car,
how Tesla, with the help of lithium-ion cells, solved this issue and why lithium-ion cells are going to become.
So if I take Tesla car out of, and then there are a lot of battery packs like this, and each pack is this dot that you see. Each
even
pack
better
is
in the future.
is a
Let's
battery,
take a Tesla
right?
cell out from the
So
battery
now if I
pack
take
and
out
break
this
it down.
cell,
You can see different layers of
so we
chemical
have
compounds
like
inside it.
different component.
Tesla's lithium-ion.
Now let's review what are those components and how it works. So if I take any battery, whether it is Tesla's battery or the battery I'm using in my illuminating the bulb in my home, or battery in my iPhone, all battery have more or less similar architecture. So if I take a battery and I cut it, so I have one side positive terminal, I have one side negative terminal. I need a framework so that electron flows. So let's check how this battery works. So I'm going a little first, right? So here the battery architecture is like this. On one side I have anode. Okay, this is called anode materials. And another side I have cathode. It's called cathode material. And in between anode and cathode I have something called separator. And in between them I have electrolyte. Okay, so I have anode, cathode, separator, electrolyte. Then when you charge your battery, what exactly happens?
We have
so I'm just going a little fast. So
exists.
when I now charge my battery, so this anode is something called graphite. What exactly graphite? We'll look more into detail. So it's like a layered structure. You can see layered structure. Okay. So this yellow dot, this is lithium ion. Okay. And on the other side, we have cathode, and its cathode is made up of transition metal oxide. Okay, so now let's say I'm now charging my battery. So when I'm charging my battery,
in between the carbon layers of the graphite, when the battery is discharged,
charging or discharge. So now what is happening here? Lithium ion coming from this anode side to cathode, and you can see this electron is flowing on the outer circuit, and we know our basic physics. When there is an electron flow, that generate electricity. Okay, so this is happening when battery is in operation.
lithium becomes a lithium ion.
So lithium ion going from one side to another side, anode side to cathode side.
An electron.
And now
the lithium ions can travel through the electrolyte.
After you say when I
to the layer collection of the battery, the opposite reaction occurs, moving the lithium back
and forth. So when you are charging, discharging, battery is in operation, lithium ion going from one side to another side, and electron goes in the outer circuit from one side to another side. Okay, so this is exactly how the battery works. So let's say just a schematic. So what we learned so far. So the schematic is that, so on the one side we have this cathode material, on the other side we have this anode material, which is like a layered material, and this is made up of something called 3D graphite. And 3D graphite we can consider is like this pencil lead. So this is pencil lead is also like a graphite. So if we take pencil lead in the microscope, you'll see like this kind of things. And we have this electron flowing in between. Okay, so this is how this battery works. So let's take one more video. So basically, so what we learned basically what we learned, we have one side transition metal oxide, another side graphite, and then we have this.
These electrons flow through the external
on the outer
circuit as they cannot flow through the electrolyte.
And through the inner circuit.
The negative term graphite layer space and get trapped there.
So this is happened.
Once all the lithium electron unstable state,
so this
as if being perched on top
so lithium wants
of a
to
hill
come out
and activate
lithium
due to this light and electrons via the loop.
When you are using this battery, so let's say I'm using my battery to illuminate bulb. So this is exactly happening. Lithium is coming from anode,
just like sliding down a hill.
And then because of electron flow, there's light is illuminating.
Thus we get an electrical.
This is the basics of battery. All these basics of battery. Now the problem is that this, okay, so before you see the problem, just a few definition in case anyone in the audience not familiar. So I'll use the term called specific energy. I'll use the term energy density. I'll use the term specific power. So basically specific energy is like how much water in the bottle. So that's like how much energy is storing inside the battery. It's like specific energy. Okay, and the water flow rate is like the power. Okay, so we'll be using this terminology. Now the problem is that existing battery is not so nice. There are so much problem. Probably you hear the news that Tesla got fire because of the battery fire, or there was news that Samsung phone was not working well because of the battery fire. Entire the car got fired just because of one the mobile phone and because of battery. Can you imagine? So entire car got fired, and then we have a lot of fire, and also recently a lot of news, e-bike fire and those things. Okay. So it means that there are many problems in the existing batteries. Okay, many problems in the existing battery. So there are some of the problem. We have the performance issue. Nowadays, if you charge your mobile phone, it will maybe last for 3 hours, 4 hours. Okay, so it will not last for 1 month, right? So and then we have a lot of other problem. We have toxic material, pollution, risk problem, cost, and a lot of problem. So the question is, how can you overcome this problem, and can AI help us to solve this problem? So we'll discuss this. Now we understood what are the problem. And I'm going to discuss this in 4 chapters. So chapter 1, the work at Brown University, where everything started. And then chapter 2 at Stanford, and then chapter 3 and 4 at NJIT. Okay, so let's say first work at Brown University. So now this is the existing battery I told. An existing battery work on 3D graphite. Now, when I started my PhD in 2010, I was thinking that why should I use 3D material? Can I use 2D material? Because 2D material is one of the natural example. 2D material is tree leaf. And tree leaf is like billions years of evolution. A lot of sunlight comes or tree leaf, and that's the photosynthesis happen. Because when you take, why leaves are 2D material, not why tree leaves is not a 3D material. That's the natural evolution, because it has more active site, right? It has more surface area. It is small weight. So then I was thinking when I started PhD at Brown, so why can't we just take this idea and implement in battery? So then I can store more energy. I can have fast energy storage. Can I do that? So then that time 2010, one of the 2D material that was very famous so was a single layer graphene. What exactly graphene? So we talk about graphite, and if I somehow can take this one layer out of this graphite, I can get a 2D layer. Okay, and for one of the first that experimentally they synthesized taking a scotch tape, and they use actually pencil lead, and with the scotch tape they're trying to pull one layer out. So this is a 2D layer 2D material, and it's called graphene, and it's very strong. Theoretically, if I can make a 2D material or a paper, even elephant can jump on it. It is that strong. Okay, so now coming to this, can I use this material for energy storage application? So then during my PhD, what I was doing, I was making this 2D material, and I was making different porous material, porous architecture inspired by this experimental. And then we made a battery. So instead of this 3D graphene, we replaced the anode side with porous material, porous 2D material, okay, porous graphene material. And now we realize that if we don't make porous, this lithium ion doesn't get absorbed on it. Okay, it's not possible. It's like you have like your parking lot. When there is a free space, the lithium ion comes more into it. Okay, so then during my PhD, I did the computation, and I showed that this is the current battery capacity, which is just only here. And then I showed that computationally that if we use 2D material with some specific topology, I can have actually 4 times more capacity. I can have 4 times more capacity. And we did a lot of other testing, mechanical testing and various other testing, and what kind of topology you need, what kind of these things, details are there and there, and why you can do that. We did all kind of analysis. But long story short, these pictures computationally, we showed that we can have 4 times more capacity than existing battery. And not just computation, then we reach out to experimentalists. They also found out almost very good matching with these things. Okay, and it appeared in several papers, and we really showed that we can have 3-4 times more capacity. It's like a eureka kind of things. Okay, so now it was like eureka moment for me. So now you see the existing. So this is a very Aragon plot. So existing, we have capacitor, supercapacitor, batteries here. We have fuel cell, and we have all this combustion engine, gas turbine, which has very high specific power, also high specific energy. Our goal is that can we make battery here? Can we take battery here? So if we can battery here, which is as good as a combustion engine, now you are driving your car, you are putting gasoline, it run on combustion engine, right? Now what happened when the Ukraine and Russia war started? You saw all the oil price went up because you need the gasoline to run that. What if I can have battery which can go like this much of energy and power? Okay, so then I can probably, the electric vehicle may be as popular as combustion engine. Now what we did at Brown, our Brown work showed that we can really theoretically, even with experimental validation, we can really go there. So I was very happy with that. Okay, so then my PhD was done. Then the question was, now can I implement it? So then come the next chapter. So I went to Stanford for my postdoc. I was sponsored by Volkswagen, and they were interested. And I was visiting a Tesla Motors headquarters, giving talk, because you can see the timing, 2015-16. That time like EV booming was happening. Like electric car was expanding like rapidly. So then I was talking to a lot of investor. I was hoping to start some company. Okay, so then we realized, okay, there is some issue. So what is the issue? So let's try to understand this. So one something called volumetric capacity, another something called gravimetric capacity. So let's imagine these clothes I have. Let's imagine this is like an energy. Okay. So now I have a big luggage bag. I have a small luggage bag. Now if I can dump all these luggage in this small bag, I can nicely organize in this small bag, then it means that I'm storing energy in a very compact volume. Okay, so that's why the unit is watt hour per liter. Okay, per liter. So then I have very high volumetric capacity. It means I'm storing energy at a very compact volume. So I can have very high volumetric capacity. But if I need a big bag to store these same clothes, then my volumetric capacity is very low. And then another is the gravimetric capacity. Gravimetric capacity is how much energy you're storing per mass. So if I have a very light, I have same volume luggage baggage, but I have a very light bag and I have a very heavy bag. And I am storing this in this bag. Since it is light bag, then I have very high gravimetric capacity, means per mass I am storing more energy, and then I have low gravimetric capacity. So one's volumetric capacity, another is gravimetric capacity. Now the question, the thing is that, so when I showed these things, so these are all actually gravimetric capacity. When I talk about this capacity, these are all gravimetric capacity. It's like capacity per mass. So now the problem is that,
Dibakar, can I just suggest that maybe, because we don't really understand all these aspects of the engineering aspects, so maybe you can focus more on the computational aspects and the AI aspects in your talk, because I know it's very exciting, but in this seminar we kind of emphasize more. It's an AI seminar, so it's not.
Okay, I'll come. I just.
So if you can just just give us the basics. We don't need to know all the details. We're not gonna build any batteries anytime soon. But use it as a nice application to get to the AI.
So we realize that this material gives poor volumetric capacity. Okay, and also lithium has a lot of problem on these things. So we have two problems. Lithium is a problem, and also low dimensional material problem. Then we started exploring all these multivalent batteries, so non-lithium batteries, and we realized multivalent battery can give us more volumetric capacity. Okay. And then we discovered that what are the material can give us multivalent battery, and we figured it out. This kind of open tunnel oxide can be very good for multivalent battery. Also, we did all the computation and experimental validation, and finally we found that this kind of material can give us more volumetric capacity for multivalent battery. So now the question is, here come the AI part. So I wanted to just spend. So now here come the AI part. So now all this material that I showed, these multivalent batteries, so this experimentally hardly 5 or 6 is available. Although computationally there are so many, but experimentally only 5 or 6 available. These experimentally we did one, hardly 2, 3 only available. But if you see periodic table, so we can have like lot more combination. So like if you see this kind of stoichiometry, Ni12WO33, it can be Ni10WO45, or it can be Ni5WO6. So it can be anything. So you take like NV from here, you take one, and so if you see this permutation and combination, we can have quaternary, we can have quinary, we can have senary. So we can have like needle and haystack problem. We can have infinite possibility. Now with DFT calculation, it's not possible to determine which is the best material. With also experiment, it's not possible which is the best material. So then comes this AI part. So then how can AI help me to discover this new materials? Okay. So just like ChatGPT, can you discover like a GPT model, so to discover new materials? Okay. So we are using this framework. So what we will do, so now from our database, we'll collect lot of data. So we'll collect lot of data. So in database like Material Project, OQMD, or ICSD. So in those database, if you see all the material that I showed here, so if you see all this permutation combination, there are a lot of data available on those things. So we can collect data from there. Then we train the generative AI model. So we use two kind of AI model. So one is Crystal Diffusion Variational Autoencoder, another is the large language model. Then we generated all the data. But thing is that, the generative AI model is generate a lot of materials, but are all the material, thousand material really useful? So we did all kind of uniqueness test, okay, all kind of validation. So we're going to talk about it. So then we predicted the property that can be useful for energy application, and then we selected final material. Okay, now let's discuss step by step, one by one. So first is the database. So we collected 44,000 data from the Material Project database, and then we took OQMD database, ICSD database. So we collected almost 44,000 data. So these are some of the variations. So we have like binary data, we have ternary data, quaternary. Of course, most of the database has like ternary data. It's like, so ternary means you have like 3 composition, like say NVWO. So like, okay, so they have 3 compositions. So those data are mostly available in the database. Okay. And also we did the experiment all mainly ternary data. So it's good for us. So now we took the database. So the next we implemented 2 kind of generative AI model. So to train those AI model. So first we implement a large language model. So we take the database, and then I'm going to go discuss step by step. So we actually haven't developed our own LLM. So we actually took this LLM model, which came from Meta, LLM 3.18b, and we fine-tuned this model. Okay, so we fine-tuned this model, and then we had this translation augmentation. From there, we do a string format and tokenization. From there, we did a prompt design, and from there, we also pre-trained this LLM with Onslaught, then with LoRa fountaining. And we kind of develop now my LLM knows that we call it like a crystal LLM because it can generate new crystal. And then my LLM generated a new crystal. So let's see step by step. So basically the goal is that to teach a general purpose language model how to write a new crystal in a CIF-like format as a text, because LLM only understands text. Okay, so our step one was to convert all the data that we got it, so convert each crystal into a text sequence. So since LLM only understand token, so and then crystal structure, we on the crystal structure, what are the information we have? We have the lattice constant. We have all the angle between the lattice. We have the atom type. We have the atom coordinate. So we converted all these materials into a long CIF style sequence. Okay, so it's like converting a 3D object into a long list of text number. Then our steps 2 is using this data augmentation to teach some crystal symmetry, because the crystal need to be periodic. So, okay, so and it need to be rotationally invariant. It need to be translationally invariant. But by default, language model probably it doesn't know these things. So we introduce all these artificial symmetry preserving variation, so that when you randomly translate atomic coordinate, or randomly rotate the structure, or randomly perturb the structure, or we shuffle the equivalent atoms. So if we do that, all these should represent the same material so that we don't get new kind of material. So basically we train the LLM so that this different version map to the same sequence distribution. So in a way we are teaching the LLM crystal without changing the architecture. So this is our step 2. So next step, now the thing is that we use LLM 3.18 billion. So now if we train this 8 billion fully, it will be very expensive. So we use the LoRa fine tuning. So we apply the LoRa lowering adaptation to freeze most of the weight in the model. And then we add some small trainable adaptive matrix. And we so that our training is much now less. Still, it took like 150 hours. So it took like 1 week to train these things. Okay, so the thing is that because of this LLM, it reduced the memory by 60%. It induced the training time. But keeping the original knowledge of LLM 3.1. And also we found that compared to others, LoRa fine-tuning, it learned the crystal pattern very quickly. So these are some of the LoRa parameters we use. And next we use some quantization to reduce the memory. We converted the whole LLM3 model into 4-bit weight using the Onslaught framework. So because of this, it compressed the model dramatically. And because we have limited hardware, it make fine-tuning very possible on a limited hardware. So in the step 5 is the training setting. So then we have our key training parameter. We use this batch size 1. We use this is the gradient. We use this is the learning rate. We use this much warm rate and cosine schedulers. So with this, our training, it was like 150 hours, 1 hour. So basically with this, we essentially tuned our LLM into a crystal language generator. Okay, so then our training objective was to reduce the cross entropy loss. So so that it predict the token that we want. So basically, category we do the cross entropy loss minimizations. Okay, and so basically our LLM is learning which number will typically follow which number and which atom type will appear after which. So it is learning all from this crystal data, and it also now learned how to preserve the symmetry. And so with this, and also it is learning how to make the stable material. So with this, our LLM learned the language of crystal geometry. And the next step we did actually sampling with the control creativity. We during the generation we use some temperature to call down the randomness so that it doesn't generate any too much random data. And then we use some the nuclear samplings. And so this makes our LLM like stable, less noisy, and more reasonable. And finally, we use some IPT, increase in perplexity under transformations. So it basically measure how much model's confidence changes when crystal is randomly translated. So with this, we did this. This is how we actually found in the LLM model. So, and we can discuss this a lot after the talk. And then we use another model. So why use another model? The problem is that this LLM understand mainly text, right? So we have to convert all 3D material like a text. Now we use another model, Crystal Diffusion Variation Autoencoder. So this is like our framework. So we train with real materials and we encode it and then we predict it, and then so we generate new material. So let me discuss step by step how we do that. So now like this LLM, this Crystal Diffusion Variation Autoencoder is like a geometry hour crystal dreamer. So it studies thousands of real TMO crystals, TML transition metal oxide, and it learns how compact internal map latent phase. Now we start from noisy and walk through the map to create new crystal structure. Now LLM mainly work on test space, but CDV works directly on 3D atomic space. So it can really understand the 3D structure. So we build our training set as a graph representations. So now each crystal we convert to as a like a graph. So each node like an atom here. So each atom like a node, and all the edges like each bonding is like our edge. So this is how we the CDV sees all these 44,000 crystal structure. So next we use this the encoder. We use the periodic graph neural network as an encoder. So it takes the atom type, atomic coordinate, lattice, and it runs the message passing through the graph, and it exchange information with the neighbors, and then it give us the latent vector. We use this kind of dimensions. And the step 3, we use the attribute predictor.
Dibakar, how big is this graph? Can you just give us a sense of a size, like how many nodes, how many edges is this graph? Do you remember?
I have to check.
Is it a million? Is it a billion? Is it? Yeah, that's what I'm asking.
No, it's not a billion graph. So it has, I think, around million. So it's
okay.
not that big graph. Okay, yeah.
Okay.
Big graph. Yeah. So then we did more steps. So we use the decoder Langevin dynamics so that it start from the noisy initial crystal grace, and it refined with the Langevin dynamics, and then it teach CDVA with what good looks like. I mean, good means here good crystal structure look like. So it minimize the 3K loss. These 3K loss it minimize, and put together we with these losses make the latent phase very smooth and meaningful. And then we have this is the latent dimensions we have. We use this is the GemNet DQ as a decoder, GNN with cutoff radius this, and 20 neighbor per atom we use. This is the hardware we use. And then this is the practical training setup. So after this, our goal is that it can generate a new kind of crystal structure. So now after this training, so if we see this thing, what kind of material it generate. So now after this training, so we started with 44. First is generate a lot of data.
Can I ask something, Dibakar? So I understand about the symmetries and the invariances that you impose, but let's say you have now from the distribution a new material, right? How do we know that material is stable, realizable? Is there any checks, any theoretical checks that one can do? I mean,
yes sir. So that is the important point. So first is generate all this data, and then the question you ask, how do you know really this is a stable material? So then we will now talk about it. So how do you know all these material are stable? So now, as Professor says, so we first generate a lot of data. So it model generated like 10,000 data. So now we do series of screening and validation. So as just Professor Kanyadakis says, to really, so how do you know they're really stable? Okay, so so what are the tests we did? So first we do some structural verification that whatever material that we have, no atom are closer than like some distance, so that no atom is very close to each other. So that's one criteria. So it means the atomic distance, one criteria. Another is that we need to have like charge neutrality, so that we generate some materials and it has some extra charge. It's not charge neutral. So then it's not a good material. So then we use something called SMACT method to verify charge neutrality. So this method just verify whether this material is charge neutral is not. So we have one check structural distance, another check charge neutrality. So from there we filter something. So from there, we get, let's say 8,000 out of like 10,000 we get. This is from CDVAE. But that's not done yet. So that's not also the answer to Professor Carnegie's question. So the next, we do more analysis. So we do something called formation energy calculation. So formation energy is like lower the formation energy is higher the synthesizability. Okay, so typically formation energy should be very low. Okay, so that we calculate. So we did that calculation. Then we do, because it's a depending on application, because it's a battery application, then we do band gap calculation. So then we did, what are the band gap? So thing is that depending on application, if it is a battery application, the band gap should be lower. Lower the band gap, it's more conductive. Higher the band gap is not that conductive. Okay, so then we select more materials. We use more criteria to exclude more material. And now the question of the Professor Carnegie's question, now more stability. Now there is a criteria called energy above hull. So it's like you consider a valley. So if it is at the lower of the valley, you put a ball on top of the valley, ball will go down and it will go at the lower of the valley. So energy above hull is how high is that ball from that valley. So that's we do calculation, some parameter called energy above hull calculation. Now, typically, it should be close to zero. It's like the ball is at the valley. So then it is like more stable. Okay, so then we do this calculation, which actually tell us whether this material really stable or not, which Professor Carnegie's question. So then we calculate energy above hull for all this material. Now probably you may be asking question that then if you do 10,000 material, 10,000 calculation, isn't it is very hard? So we actually develop a forward machine learning model. So we develop a machine learning model. We actually train that machine learning model with some known parameter. Okay, if the material crystal structure is like this, then energy above hull is like this, So that machine learning model, NN model, can predict this energy above hull, all these property that I'm talking to distinguish which is the most useful material. Okay, so with this machine learning model, we can determine all these 8,000 materials properties. Now from there, we do further screening. So after doing all these analysis, you can see that finally from 1,000, we end up only 42 structure. Okay, so that was the very important question by Professor Carnegie, is that not all are stable, right? So you see that first we get 10,000, but finally we get like 42 structure. And also another thing is that out of this 42, 5 really contain oxygen and 37 don't contain oxygen. Although you train the generative AI with oxygen containing material, but the material that you are getting may not have oxygen. So okay, so we get 5. Now we have to see all these 42 that we are getting, is it really new or something is really there in the database? Because if all the 42 is there in the database, then your AI is not much useful. Okay, so it should be brand new. So we saw that out of 42, 21 structure is there, which is very similar. So if it is like, if the AI predictor structure is ABO3, maybe in the material structure A2BO3 is there. So it's not like exact material, but similar material is there, but not exact material. And remaining 21 is like a brand new. There is no material. Okay, and also we tested that all these calculations we stated, they are very stable. So then, then we can out of this, so we can really see that. So these are some of the snapshot of the material that CDVAE predicted. And this material, it doesn't exist in reality. No one synthesized, no one even computationally predicted, and it can be experimentally synthesized. Okay, so this is like CDVAE structure. Now let's check what LLM does. So LLM also generated very similar, almost.
Dibakar, can I ask a follow-up question? So, because these look like the previous interesting structures. Are these very surprising results, or is it like for a material scientist would see this and say, well, it's a little perturbation of what, or is it really surprising?
It was really surprising because like 21 structure and all those 5 structure which contain really oxygen, so they are even not similar also were there in the literature. So we found really completely new kind of structure which has like porosity, which can be used for multivalent battery it sounds stable. So it was not exactly similar. So it was kind of brand new, but maybe only 5 or 6 it was brand new out of like 44 training.
But we still don't know if they're better than the conventional materials.
I'm going to talk about that also.
Okay,
yeah.
all right.
That's
I think I'm setting you up for the next slide.
yeah. So now let's talk about the LLM. So whatever we saw, the CDVA does. Now let's talk about LLM. So LLM also first give almost very similar, like 1,000 structure. But when you do this first set of uniqueness stage, uniqueness means the crystal should not be closed, the charge should be neutral. Then after that, only 1,000 remain compared to CDVAE. And after that, we do all kind of analysis like energy above hull, this formation energy, all this kind of with the forward machine learning. And after that, we only end up only 13 structure. Okay, only 13 structure. And also this 13 structure, so these are 5 of those structure. It doesn't contain oxygen, but they are very stable. It might be very useful for for energy storage application. So what we learned so far, that CDVA give us 42 structure, LLM give us 13 structure. Okay, so these are the structure, and let's dig little more. So what we did kind of, so this is the question that Professor Kanye is asked, which is very important. This is the parameter which is really stable or not, and closer to, and if this value is closer to 0, it is like a more and more stable. So we got like in this range. So these are the material which are very stable, and most of the LLM predicted material is in this range. CDBA also is in this range. So we got material which are very stable, which was the professor's question. Okay, so we got very stable. Now we got another, same analysis we did, formation energy calculation. Here's another interesting thing we did. We did this crystallography analysis. So what we found that, so as you know, in crystallography, we have different crystal structure. So we found that most of the LLM predicting material, it has a very, LLM try to predict, even I don't know why it does that. So, your input will be very useful. LLM try to predict crystal, which has the R3M or CM, this kind of crystal structure, while the CDVA, it try to predict crystal, which has crystal structure like P1. So it means that different generative AI model has a tendency to generate different kind of crystal structure. I don't know why is that, so maybe it needs more study. So, okay. So now another things we did. So now, as I was telling, that some structure, so as Professor Kanye is asking, is this material really new, or is it something that a similar thing exists? Okay. So this was the question he's asked. So as I was telling, so some materials, maybe 10-15 material was completely new, and at least 5-6 like brand new, which is not even similar exists. But some materials, similar material was there in the database. So what we did, we thought, okay, so those material which is very similar, let's do some comparison. So if you see this thing, now if you see this orange, this is like a material project database, and this material is there in the database, and people have studied it. And this material, which is like a which our AI predicted. It's not comparing apple and apple. It's like reddish apple and red apple, because here we have 6 fluorine and here we have 8 fluorine and here we have like 2. So, but it's very similar. So we see that, comparing similar structure, AI predicted material see less energy above hull. Okay, so we did this sim calculation and see that our predicted material is very stable. So after doing all those things, so we propose that these 5 material as the most stable, is the most stable, and it satisfy all kind of checklist: stability close to 0, formation energy very low, band gap almost 0, very stable. So all kind of checklist it takes, and we propose okay, this 5 material which has nothing similar also exists. This can be very good. It has open tunnel, it has oxygen, and it can be very stable. So now coming to again Professor Kennedy's question, so stability. So there is another check of stability. It's called phonon structural analysis. So phonon dispersion analysis, it can also give kind of dynamic analysis. So when during the experiment, will it be really stable? So we also did phonon analysis on all these 5 material. Okay, so we didn't, because this is very heavy calculation, so we didn't do for all material. So we check that if the phonon analysis, if there is no something called no imaginary note, then it is very stable. So we also did phonon analysis, and we found that these materials are very stable. So now, coming to again Professor Kanedi's question, so now I have this material and I am telling that this material will be synthesizable, but how to really synthesize, or can you really synthesize? What was the guarantee that I can synthesize? So we are thinking this question also, and what we did, we are studying RAG, retrieval augmented generation. So now thing is that as this material nobody synthesized, nobody studied, it's brand new material. So we are thinking, is there any precursor? Precursor means, let's say I have Mg2C2O F6. So is there any precursor? So let's say MgCu or CuOF6. Is there any precursor that people synthesize? So what we are basically doing, so let's say my AI predicted material is K2C4F10 and its precursor is KF and its precursor is CuF2. So we did this RAG coding and try to mine data from literature, how these precursor, what people did experiment, how they did experiment. And from there, we are trying to get an idea, okay, people did experiment this in certain way. Then if I want to do experiment of this, what are the way I can do experiment? So we did all these RAG. We are trying to develop a multi-agent RAG systems, developing a multi-agent RAG system. And we are trying to collect our own data from the database, not relying only material project database. Because when you mine literature data, you can say that, okay, people really did experiments and synthesize, not just computation. Maybe it's more reliable. So we are mining data from literature, and then we develop some framework that, okay, if we want to do, let's say you want to synthesize 20 kg of K2C4F10. This is AI predicted material. So then what are the things you will do? So then from the literature, it try to understand, okay, how similar material was synthesized, how precursor was synthesized. Then it can give some idea, okay, then to synthesize this material, you can have temperature, these, you can have pressure, these, you can have this much pressure, it may need this much time. So you can use this kind of synthesis, reaction might be this, okay, and also it gives some safety criteria. Oh, your structure has, if you see this structure, your structure has fluorine, it might be flammable. So you have to take care of this, precaution. So with this, this is we just started. Your suggestion is very much welcome. We need your help on these things. So to give some idea of how this AI predicted material, as Professor Kanedi says, was the criteria, was the guarantee it can be synthesized, was the guarantee it can be. So maybe we can give some idea how it can be synthesized. So a long story short is that, so we can, of course, this is a very preliminary talks we did. There are a lot of things to do, so we can develop a, energy kind of GPT, and, leading group like Crunch group can help us so to predict these things, and it appears in also Greek media. So I put this. Okay, so now I want to briefly discuss, so your input is very much appreciated. How can we translate it on quantum material and biological material? So now, reason I wanted to show you, I recently got an NSF DMIF grant on these things to apply the same technique on quantum material. The reason is that although there are a lot of research on quantum computing, and as you know that current quantum computer has only 1,000 qubit, but we need like we need like millions qubit to make it work. So, but what's the problem with the quantum computing, which actually proposed in our DMREF proposal, that the problem is that I'll just briefly tell, and then so it has something called electro-optic coefficient. The thing is that if you apply electric field, it refracting index change. And so we need quantum material that can have high electro-optic coefficient. High is something called Pockels coefficient. It means that if you apply electric field, the refracting index change a lot, and you can tune the refracting index. This is one of the criteria. And other thing is that it should work. It should be integrated with silicon, and it should work at cryogenic temperature. Okay, so now the problem is that which material shall I use to get this done? Okay, so now currently, as I said, people use LINB03, and it has problem with integrating silicon, and it has only 1,000 and we want like more and more and more, and we want it to work cryogenic temperature. So again, the same like energy material problem. We have infinite material space. People use something called perovskite, AVO3. And then if you see your periodic table, and we have alloy systems, you end up getting like infinite combination of material. And the problem is even more complicated because now you tune the material, you apply some strain, you apply electric field, now you have to know which electric field, how much electric field shall I apply, how I will tune the refracting index. So this is very similar like needle in a haystack problem. And our hope is that we can apply the same framework, so you can give us more suggestions. And now only thing is that we have to now, instead of energy material property, we have to have focus on other kind of property, like the property I mentioned, electro-optic property. So in that way, probably we can use the same. But here is the problem is that unlike energy material, so the data because for generative AI, we need a lot of data, right? The last one I showed, we started 44,000 data. But the problem is that there's not much data there for electro-optic material. And training a machine learning, this forward machine learning model to predict electro-optic property is not there yet in the literature because there is not much data to train it. And doing DFT calculation is very, very crazy expensive. So there are a lot of things to do. So this is one thing we are doing. And another things because we are doing is biomaterial. And this is something I did during, again, my PhD at Brown University. So what I did during my PhD at Brown with a professor called Robert Hart. So this green thing is called graphene. And this red is the water. If you put graphene inside water, it come out and it can wrap. So with this framework, during my PhD, we developed something called graphene enveloped nanoparticle for drug delivery purpose. Now, again, the same things, so as Kran Group is doing a lot of work on this bio. So now, as you know that for drug delivery purpose, when you design this nanoparticle, you have like so many different parameters, like the nanoparticle size, its shape, its elasticity, its stiffness, its surface chemistry. Okay, so yeah, there also we have nearly like infinite design space. So how to design all these different ways. Okay, so this is also kind of needle in a haystack problem. So can I use this kind of framework? So I just got some seed gun to give a try, training with the biomaterials and this kind of things. So this is just I'm doing, and I look forward to getting your feedback. So yeah, so long story short, so I think there's an enormous opportunity to develop a generative AI for discovering new material, not just for energy, for quantum computing, for biology, for various fields. There's many opportunity, and I look forward to giving your suggestion and feedback. So thank you so much. Thank you so much for your time. Thank you so much, Professor Kanyadikis, for the opportunity.
Thank you, Dr. Datta, for presenting your work. We can now open the floor for questions. Do we have questions for the author, the speaker?
Hi, my name is Kamal. I have a question. I am from Brown Grants.
Yeah.
You are taking the LLM model from, I think, Meta. How do you know that the new data set and the old data set is not conflicting each other?
So new data set means the data I'm generating?
Yes, and the old model data set, because we don't have the access to that, I believe that.
Oh, so the model, so you're saying the material that I'm generating and the material that I trained?
No, the initial LLM model, they use some data is there to train that model. So that data set and the new data set, is it same or it might be conflicting each other?
No, I don't think it's conflicting because we use this LLM and then after all the fine tuning, because all the predicted material, so we tested all for stability and this thing. So I think it will not conflict. It's not conflicting. Yeah. And how do you know? Because our new predicted material, we check that, all kind of checking we did. So it's giving all stable materials. So I think it will not conflict.
Okay. How do you ensure that it is not giving the result from the previous part, like initial model?
Oh, so you are saying how do you ensure that my fine-tuning is really working, or?
Yes.
Okay. So no. So no. So we really didn't we took the previous model and just ran it. Because we had our assumption that if we just take the previous model, probably is not trained to understand exactly our crystal structures. Okay. So from the beginning, actually, so we really assume that it will, and it is not good for understanding this crystal structure, because that model really nobody really tried to generate, as far as we know, generate a crystal structure. So we realize we have to fine tune it, we have to optimize it for our specific purpose. So maybe I think you're a good session. Maybe we'll take the whole model and just run it and see how it works. So, but we assume that we have to fine tune it for exactly for our purpose.
Okay, yeah, thank you.
Thank you, Kamil. I have a question. Yeah. So when you train the generative models on a bunch of structures or materials from an existing data set, did you try to condition it to generate stable structures, or in that data set were all the samples stable structures? Did you do a conditioning for that?
Okay. So basically you are saying that, let's say I have this because after this I am generating, and after this I am doing all checking. So basically you are asking, can I just plug here only?
Yes, and just condition it. Yeah.
My final product is the stable structure.
More likely to be stable. Do you do something
more likely
like
to
that?
be stable? Yeah, that's a good idea. But we thought that might be very computationally expensive. So we first wanted to generate data, and then we do all checking. We thought that it might be computationally more optimal. So that's a good idea.
Yes, I asked because there is a huge literature called conditional generative models.
Okay.
So maybe that is just the question. Thank you for answering.
Okay. No, we'll check that. Yeah, that's a good suggestion. Thank you so much. Yeah, thank you so much.
Yeah. Hi, Dibakar. I have one question too. So I think on one of the slides you were mentioning that the latent space that you learn in the CDVAE is smooth and meaningful. So like, could you explain what do you mean by that? So are you suggesting that when we interpolate in this latent space, we're able to predict structures which are more stable? Is that the kind of interpretation that you have?
Yeah, that's kind of interpretation I have. Like, it's not giving me although it's giving me like 1,000 structure, so and after that, after a lot of filtering, I end up getting very few. But even those 1,000 structure is not something, let's say one structure is weird, like it will never happen, like it's not very weird. So my meaningful means I'm taking that even the 1,000 structure generate is very meaningful. Like so if it's like H2O, it looks like H2O, may not be exact H2O. So that I wanted to say that here.
Okay. Yep. Thank you.
Dibakar, I have a couple more questions for you.
Yes, sir.
Yeah, that's very exciting, and you were able to generate real results. I was wondering on the data collection part. So, for example, for materials, we know that there's a materials genome project.
Yes, sir. Yeah.
Do you have to go to that, or at what level of scales do you collect information? Because then by analogy, you can go to the human genome and so on. And for, if you want to design something, then you can go, but do you have to go that low, or, you know what I mean? At what level of you thresholding the information?
Yeah, so that's the most important part. So for these projects, so all the material we collected for this material and genome project, and also some of the material we collected from another called OQMD, Open Quantum Material Database, and also another database called ICSD, International Crystal Structure Database. So we use these three databases, and for this project, to be honest, we just collected data from the database. We didn't check anything else. So all these 44,000 collected all three databases. We use whatever data is there. But then, so here I'll need your suggestion. Now we are actually doing this augmented generation. We are actually trying to mine data from literature, and as if we are creating our own database. So this will have database from this database from the material project. Plus this will have database from all the literature, all the what human did, and we first develop our own database for material project, for literatures, whatever, and then probably we use that and for our AI model. And another important point that you mentioned, because when I'm using this database, this database all are computational. None of them are experimentally, like most of them are computational. They haven't experimentally synthesized. So now if I use some data that is also experimentally synthesized, so then I'm starting with the data which I know that experimentally synthesized, which I know really stable. So then maybe what Vivek was asking, that maybe my generated material will be towards more stable. So I think this is something is very important, like which data to use, how to efficiently use data. Yeah.
But from the genome project, it's kind of useless to you, or at some point in the future, or you will have it in your multi-agentic
No, it will be, we will keep that also. In addition, we'll add data from the literature which people do the experiment. So we'll add both computational data, we'll add both experimental data, and then we'll use that to train our AI model.
Yeah. Can you say how you organize your database? For example, Marcus Buller at MIT, he has this knowledge graphs, right? And then from the knowledge graph, you have a curator for this, and so can you just speak of that? Is that how you organize the database, with different knowledge graphs, and then you have a curator of all these graphs together, of all the knowledge graphs together, or you haven't got that to that point yet?
No, not that point yet. We just mine all this data, I think, because 40,000 data was okay to handle as for us. So yeah, so we just took the data from this material project and we just ran it. But at the next level, we'll implement all the idea I got from your suggestion and Crunch group member suggestion. Yeah, so that I'm planning to implement, because
also something else about the diversity, because your early work where you show the variational autoencoders and other people's GANs, I suppose they generate certain structures. These are very, very different from the LLM, right? That's what you showed.
Yeah.
In your multi-agentic system, are you trying to have different LLMs, or are you just staying? Are you going to use diversity as a criterion to get to all these classes of with oxygen, without oxygen, and so on that you show? I thought that was very interesting finding. But do you use that? Are you going to plan to exploit that in the by including diverse LLMs in the multi-agent system?
That's that we want to do. Yeah, including diverse LLM. And we found some tendency also, like as I was telling, like different LLM try to generate different kind of crystallography they try to follow. We don't know why that, but we want to explore that also. So we'll implement different LLM and we'll try to generate more data, and we'll see. Yeah, and we'll seek your advice.
I think the VAA is probably with the prior that is chosen locks into certain structures, so that's why probably it's not expressive enough.
Yeah, exactly. Yeah.
Let's see, Kyle or Juan, do you have any questions? They're building multi-agentic systems. I don't know if Kyle has any questions.
Yeah. Thanks for this talk. It's really cool. Maybe just one question, since for the generation part you use LLM to generate the structures. One question I have for that part is that the LLM, the use of the LLM here is only to generate these structures that has a specific structure that you want. So why is the motivation to use a off-the-shelf LLM to fine-tune it? For example, you use Llama to fine-tune it, but you do not need to use the other capabilities of this LLM. For example, Llama speaks French, and it also knows how to write poetry. You don't really need that part of the LLM's capabilities. You only need it to generate these text sequences that represent the crystal structures. So would it be another approach if I just, I don't know, train everything from scratch? Or so there how do you think of this excessive capabilities that the LLM has, but that is not used in this workflow?
Okay. So basically you are asking this, I have LLM, but certain part, like the one you mentioned, is good for poetry, and I want to do poetry. Why don't I just use that part? Like, So basically, yeah. So that's a good suggestion. So no, we haven't tested yet, but this is something, you know, I'll keep this in mind for future work. We haven't thought that way. Yeah.
Yeah. Thanks.
Yeah. I want to emphasize. I think there was another paper by Microsoft and one paper by Google Group. So two paper those two company published. They also did the similar work, like material generations. Although there are a lot of controversy. So I think this is a very new, exciting field. And
Yeah.
if I can get help from Crunch Group, we can implement many other fields.
Thank you, Kyle. Do we have any other questions for Dr. Datta?
Hello, Dr. Dibakar. Yeah, so basically, I was thinking from the foundational aspect of the whole thing, basically. So, like you have already mentioned about that in your talk already, that basically these like electro-opto properties of the cryogenics is very different from the normal materials, the crystallographic materials that you have used in your database, right?
Yeah.
So I was just thinking from the foundational aspect that if we try transfer learning at certain point in time with already established database that we have, do you think that that kind of transfer learning will help specifically for the case of cryogenics in terms of maybe for the quantum computing, let's say? Because foundationally that won't help, right? We will be needing a whole new approach in order to work with this specifically for the cryogenics, specifically if we mention, because cryogenics work, as you know better than me, I've just read a couple of things about it at millikelvin temperatures, right?
Yeah.
And that is very different from the foundational aspect of crystallographic materials that deals with deformations, mechanical deformations and stuff like that. So from that point specifically, it's vastly different from design spaces aspects, right? So that is the major challenge, I guess, in terms of in implementation specifically. Even if we at certain point in time we try to go with the transfer learning. So as far as my experience is, it won't be working, right?
No, so that's an important point. You know, I was telling that when I was telling these things, this data. So, and Professor Kaniatek is telling, let's say we have this material project, you know, can I just use it? Now, that's the important point also Professor mentioned. Now, for this cryogenic, as you mentioned, this cryogenic temperature. So now we need, now when you run DFT calculation, density functional theory calculation, so traditional DFT actually 0 Kelvin DFT, right?
Yeah.
So now let's say I do DFT calculation, which I'm currently doing to calculate this electro-optic coefficient, Pockels coefficient, which currently very low, and my goal is to make it very high. So now the DFT result that I'm getting, I can say that this is a 0 Kelvin result. All the result I'm getting 0 Kelvin. We can say cryogenic. Okay. So now I can, if I use that data to train my this AI model, so as if I am training my AI with the cryogenic data. Okay. But the problem is that how many DFT will you do? So now if I want to do 40,000 DFT for this, even for one things, so calculation is crazy expensive. So that's one of the hardest part of these things. Now here actually we can, I'm trying to do, so I'll talk to you more on these things. So what I'm trying to do here, I'm doing DFT calculation as much as I can. Although DFT for electrooptic property in literature not much there. We did a lot of literature survey, not much there. So probably we do something, maybe we do some forward machine learning and maybe we can generate more data. So I don't know. So we have to see how to progress, how to get the data to really do this thing. That's why AI for electro-optic material prediction is not there in literature. You can correct me if I'm wrong. It's not there that much. One of the challenges is the data. So yeah, so I think all your point is very good that transfer learning may not work because it's the cryogenic. So we will look into this and we will consider all these points. Thanks.
Yeah, because even the augmentation won't help in this case, specifically if I mention the augmentation of the data, even if you come up with some DFT calculation, let's say 50 DFT calculations manually, even that data set won't be enough for the generalization of the aspect that you are seeking.
Yeah, that will not be enough. And it's very challenging. This DFT calculation of this is very challenging. I'm currently doing so. We can talk more.
I can only guess.
Thank you for the question, Saeed. I think let us wrap up this session and move on to the next talk. And thank you again, Dr. Datta, for presenting your amazing work with us.
Yeah, thank you so much. Thank you so much again, Professor Karniadakis, for this opportunity. Thank you so much. Thank you so much.
Thanks for coming.
Thank you.
Maybe Arihant, okay, could you please try session mode? Yeah. Perfect. So Arihant Patawari is a research scholar at Indian Institute of Technology, Patna. He would presenting his work on a semi-analytical neural network framework for a 2D time fractional reaction diffusion model on a bounded domain. With this, I invite Arihant to present his work.
Yes, thank you, Vivek, and a warm thank for the Crunch organizer group members. Now, I will start my presentation, and the title of my presentation is a semi-analytic neural network framework for 2D time fractional reaction diffusion model on boundary domain. So these are my outlines. Just I will start from preliminaries and I will end with the numerical experiments. So in this preliminaries, I will show the Lively Capito fractional derivative of order alpha. As we know that this fractional derivative is non-local operator because for finding at the derivative at point t, it will use the previous values of t to find out the value of derivative at point t is equal to t naught. So similarly, equation 1 is for alpha lies between 0 to 1. We can also generalize it between alpha up to from n minus 1 to n. And we can take the formula, which is also easy. And further, I will show the Riemann values. Fractional integral order alpha is alpha greater than 0 is defined in the equation 2. So why I will start and what is the motivation of this work? So I will just give the insight of that work from point 1. So as we know that automatic differentiation is used to compute the integer order differential operator. So using automatic differentiation, it can use classical chain rule to find out the integer order differential order, but it is not applicable to compute the fractional order derivative. So we need to some numerical schemes to implement into the physics informed neural network. So that is the first motivation of this work. And further, we will use some trial solution to involve into the physics informed neural network to enhance the accuracy of the prediction solution and reduce the error between the U exact and U neural network prediction solution. So after that, how would I generate the trial solution? That is also a question, and that trial solution will improve. That is also a question. This question I will discuss in the further slides. And after generation of the trial solution, I will show some. So in the slide that the convergence analysis and sufficient condition for the Edomian decomposition method for the chosen model problem. And finally, I will give some insight of generalization error bound for physics informed neural network, which involve the semi-analytic method for the chosen model problem. So I will begin with some highlights of existing literature. So this first one is well-known work, which solves the first novel meshless physics informed neural network that solves the linear and nonlinear PDEs with less number of data. And further, similarly, this Karniadakis group is also solves the fractional PDEs, fractional ODs using the fractional pins, where F involves the numerical methods that tackle the different fractional differential operator, and pins use the automatic differentiation for integer order, as I have already discussed. And third one is a very good survey work on the physics informed neural network, that gives some insight of the fractional differential equation, integral order differential equation, and integral and stochastic PDEs. So I have also seen some generalization error bound in the paper of Siddharth Mishra and Molinaros. And finally, I also read the paper F-pin DPonet, where they used the operator learning framework for multi-term time fractional mixed diffusion wave equation using physics-informed neural network. So in the very first paper, fractional F-pin, they have chosen that the initial condition is 0 and boundary condition is 0, and they have also used them. They have also used some kind of hard constant used in the neural network solution to measure the boundary condition and initial condition. But sometimes it is very difficult to measure the boundary condition and initial condition. To tackle such consider such problem, I have chosen this problem, where if I multiply with t with the neural network solution and so if I will put t is equal to 0, which will not match with the initial condition because their initial condition is non-zero. But in a fractional plane paper, they have chosen that initial condition is 0 and boundary condition is non-zero. So for those consideration case, I have chosen that initial condition non-zero, and we are not using any kind of hard constant in the neural network solution. So here is the positive constant. B is a sufficiently smooth positive function, and similarly f is its source function, and Sx is the initial condition. So after the model problem, how the data generation will work, or how we will generate the data. So if in the equation 3, if this part the a del u plus and minus bu, if I take this part into the left hand side, then the LU will be the difference fractional operator, and RU will be the left hand side of a del u minus bu part, and f is the source function, where L considered as a linear operator, linear fractional invertible operator. Why this should be linear invertible operator, which will show the insight in the equation 6. And R defines the remainder of the linear operator, which I have already discussed, that this will be A del U minus B. So the decomposition solution can be written in the following form, where Ux can be written in the summation of I is equal to 0 to infinity Ui. So these decomposition solution we will find from the equation 6. Where if I will multiply with L inverse operator in the equation 4, then I will get the equation then I will get the U0 xt, and further with the help of the previous information of U, I will find out the next information of U using the L inverse operator. So finally, I will define the series solution in terms of phi, where phi p xt is equal to some summation form of I is equal to 0 to p minus 1, where to match the solution with decomposition solution, I will choose phi 0 is equal to 0. So see, from equation 6, equation 6 is basically using the initial condition. Basically use the initial condition and source function. So there is no involvement of boundary condition. So that is why I am saying that the ADM requires only initial condition and do not rely on boundary condition, which make it naturally applicable to PDs on infinite domains. So similarly, the 7th point, if I will increase the series sum up to infinity, the partial sum will converge to the exact sum for the infinite domain of PDs. So we can learn. We can simply understand from the boundary value problem, OD problems. So where boundary value OD problems, where the OD is defined as LU is equivalent to u double dash is equal to bx ux plus fx, where boundary condition is defined. And we assume that bx is greater than equal to 0 and sufficiently smooth function in the given domain from gamma to delta. So if I again multiply with the L inverse operator, so if I will implement L inverse operator into the equation number 8, then I will get this equation. So this equation usually in general uses the boundary condition. So I will get the UX solution using that boundary condition. Boundary condition. So the above process similarly used for the initial data above process is used for the PDs, which involves the initial data with the unbounded space domain. So that means the ADM is only applicable for the unbounded domain. So here we will convert this unbounded for the unbounded domain PDs, we are converting into the bounded domain of PDs. So that is why we are using the sufficient condition for bounded domain, where we will use the infinite order compatibility to match the initial condition with the boundary condition, so that the ADM will work for the bounded domain also. So convergence analysis, I have taken that convergence analysis from that paper, Convergence of ADM Method, which is written in 1989. So there they said that if the lemma H1 and H2 satisfied and the operator F is hemi-continuous, then the solution will converge to the exact solution. So where F is defined on the Hilbert space and defined in such a way F is equal to minus R, then operator is hemi-continuous, which we have already proved. And we have also proved the lemma, second lemma, where H1 and H2 also satisfied, which is the Lex-Milligram theorem, which provides the uniqueness and existence of the solution. If we include the both lemma, then the decomposition method for applied on the 3 will converge to the exact solution. So till now we have generated the ADM based data.
Can I ask a question? So the VAEs here, the basis is Adobean polynomials, the expansion. Did you say that? I missed it.
Where, sir?
You didn't talk about Adobean polynomials, so I was wondering if you refer to Adobean method.
Yes, sir, Adobean method, yes, sir.
But you didn't refer to any Adobean polynomials explicitly, so I was wondering.
So, sir,
if you go back in the expansion, right, for the partial sum.
Yes, sir. Yes, sir.
So right. Not here, but when you had, I saw some phi or phi somewhere.
Yes, yes, sir. This one is phi.
Okay, so this is right. That's what I meant, right?
Yes, sir.
So are these that define the Adobean polynomial method?
Yes, sir. That is defined for the ADM method, sir.
ADM method, yeah, okay, yeah. Because I don't know people know that. I mean, it's not a well-known method.
Yes,
only
sir.
People who do fractional PDs know that.
Yes, sir. Yes, sir. But it is well known for the unbounded domains, PDs for unbounded domains. Here we use the ADM for the bounded PDs.
Yeah, I know. I'm just trying to put this in context.
Okay.
And there is another point here. Just I want to note that this may not be a polynomial also. For example, these UIs are being generated from the equation 6. Can you go to the equation
So I
6?
saw that it doesn't have to be polynomial. You're right.
So this L has to be invertible. In addition to that, so the L inverse AF has to be found out by using semi-analytical approach. That's why it is a semi-analytical approach. Okay. So basically, the next theorem is providing the convergence of this semi-analytical approach, and then we'll be taking the partial sum. That means the finite sum of this one, and then we'll be taking that one as a initial guess roughly for generating the pin and ADM based solution. That will come later.
I see. That's good. Yeah.
The convergence as p goes to infinity from the partial sum will be clear from this equation 6, the equation 7, where the partial sum is mentioned. Okay. Okay, you
got
can
it,
go ahead.
Yeah.
So can I proceed further?
Yeah, so that basically defines the ADM method for those of you
Yes.
who've never seen before without using polynomials, like Pradeep said. Yeah.
Yes.
So can I proceed?
Please.
So further, I will try to combine the pin framework with the ADM data. As if I will remove this part, ADM-based data generation. If I will remove this part only, then this is simple fractional pin, which 2019 they will developed and solve some fractional PDs, and basically they use the L1 scheme for the fractional operator and automatic differentiation for integer operator. So further they combine this numerical scheme and automatic differentiation, and using for that they define the loss function, check the accuracy. If not, then update the parameters and provide that parameters, again update in the second iteration further for. So next I will involve the ADM data. Further I will involve the ADM data into the loss function. So this ADM data initially start with the initial series sum p is equal to 0, p is equal to 1, and up to p is equal to some finite number in the coding. So so initially it is not a good data. So we used some kind of weighted parameter into the loss function. So in the initial phase of the series sum, I will provide the lambda 4 in such a way. Lambda 4 is very less than lambda 1, lambda 2, and lambda 3, so that it can generate the weight and biases. It can generate the weight and biases such a way that the U can learn from the UADM solution, and which also take care that the L of PD, L of int, and L of BD. So L of int can be defined in such a way. So where RPD is defined using the residual part of the PD, and RI is defined using that initial condition of part, and similarly RBD is defined using the boundary condition of part. And finally, the ADM based data is defined in such a way that the neural network solution can learn from the UADM solution. So similarly, this case defined for the series sum up to p is equal to 1, up to p is equal to 2, p is equal to 3, and if we increase the series sum, we also increase that weightage lambda 4, so that the complete loss function is also dependent on the LADM for the better solution. So finally, we have provided some generalization error bound on the ADM pin. So where that we have shown that the generalization error phi 2, which involves the U minus U neural network over L2 norm, which is bounded by some RINT, RPD, RBD. As RINT, RPD, RBD are taken from the Siddharth Mishra paper. Similarly, from the quadrature bound, that if I will increase the number of points, that that will go decreasing as number of point increasing. So finally, we have also provided some convergence that if number of point increases, if I am choosing uniform number of partition, and based on the number of partition, uniform number of partition n increases, that the error bound is going towards the 0. So for the numerical experiments, I have chosen.
Can you go back? Sorry, can you go back to the theorem?
Yes, sir.
Where? No, before. Sorry, the bound. Where is the ADM in the right hand
Yes,
side?
sir. Actually, P is not involved, but we are providing in. Sir, directly P is not involved in this proof, but as we see that LPD is involvement of Lu minus F. Okay, so we have proved in the ADM part that Lu minus F is converging toward the exact solution as number of series term increases. So we are saying that this in the limiting case of P, if P goes to infinity, this is going towards 0, and which is also matching initial condition and boundary condition.
So R here is not the discrete residuals, is the continuous residual for
Sir, here Rx is the continuous because P we have.
Okay. Then okay, but yeah, okay, fine. All right, thank you.
And finally, we have chosen some kind of hyperparameters to train the model where activation function optimizer, and we have chosen the maximum epoch, but to stop the iteration, we have provided some tolerance on the loss function, and we have chosen hidden layers is equal to 4, and in each hidden layers, we have chosen 64 number of neurons in each hidden layer. So for checking the ADM and ADM plus spin algorithm, we have chosen this problem where alpha is equal to 1. See, alpha is equal to 1 and initial condition is sin x and sin y, but the boundary condition is 0. So the result based on this problem for the ADM, since ADM is not involving the number of, since the ADM is not involving the number of partition for the convergence, so the error corresponding to the ADM is almost same if I'm increasing number of partition. Fractional pin is not involving the number of, fractional pin is not involving the series sum. So in the table 1 and table 2, you have seen that fractional pin have same error for table 1 and table 2. Since ADM pin is involving the series sums P is equal to pin, P is equal to 2. So if I provide P is equal to 1, then the error of the ADM pin is kind of something. And this is also decreasing if P is equal to 2, because I am providing some convergent solution P up to P is equal to 2, then ADM plus pin is decreasing error again. But F pin from P is equal to 1 to P is equal to 2 is not decreasing because they are not using any kind of solution up to P is equal to 1 and P is equal to 2. So further we have chosen some two-dimensional time fractional problem having a singularity in the time. See, the solution t to the power 1 by 4 sin x sin y having some singularity in the time. So in this problem, the ADM is also similar results. ADM will give the also similar result and 20, and pin again pin for table 1 and table 2 is same result because it is not using P is equal to 1 and P is equal any series sum, and ADM plus pin uses series sum at P is equal to 1 in the table 1 and P is equal to 2 in the table 2, and it is also decreasing from 4.1 into 10 to the power minus 2, 2.1 into 10 to the power minus 1, and it is also decreasing as number of point is increasing. So this is our aim to show that theoretically an increasing in a specific number of P, the ADM pin is also decreasing, which we have shown in this example also and this example also.
Why can you not do P equals 10? Is it too expensive?
Yes, sir. It is expensive in terms of ADM and also ADM plus pin, sir.
Because it looks like a linear decrease. It looks like a linear decrease with P here. You double it and the error is half, but still very big error. Okay, just keep going, keep going.
Oh, okay. So finally, this is my references which I have used, and thank you, sir. Up to we have ended the slides. So any questions?
Thank you, Arihan. We can ask more questions to the speaker.
Yes.
So you can definitely take P equal to 10. That is possible. It will not going to increase the computational cost compared to the neural networks. That is possible. But our aim is to take P as much less as possible, and then after that, you need to go to the neural network and try to show the improvement compared to the neural network itself, not by ADM.
So I kind of missed the point because so basically you tackle the problem using both the Domin method and the neural network basis, but I think what you need to find is the right balance, right? How a big P would be so that the network, and then how big of a network you have. Am I right? Or am I totally off?
Yeah, I mean, if we increase P, definitely it is going to converge. That we know because you have already provided the convergence. But point is, just wanted to give a initial approximation before going to the neural network. That is the main aim, roughly.
Yeah, no, I understand that. So that's a good thing. It's like a prediction correction type method, let's say. But the question is how good the prediction would be so that overall you get the best accuracy at the end without breaking the bank, without incurring too high of a cost on either side of the Adomian method or the neural network. And then you need to compare with the baseline, FPIN everywhere, both accuracy and I mean, of course, you compare with 2019. Since then, our group and other groups have published other methods where you don't actually need to do the L1. You can just do the derivatives using integrals, using just the integration. Quasi-Monte Carlo, for example, we published a paper where we show how to use to do all these derivatives using Quasi-Monte Carlo. And Podlupny also has a method for that. So then you don't need actually to have a structure grid like we did in 2019. But you, I think the hybrid schemes are good if you beat the baselines, beating it in terms of accuracy and cost. In 2019 paper, we saw that there's a kind of stagnation of the convergences. That's probably because we didn't use the right optimizers at that time. Now, if we revisit this using second-order optimizers, I think we'll have better accuracy. But what I'm saying is, it's an interesting study. You have a good idea, but it's kind of incomplete because I don't know what to conclude from this.
See, I mean, so there is a problem with the fractional derivatives. Like it is having initial layers. Initial layers in the sense its derivatives are unbounded. First derivatives or second derivatives are unbounded. So if we use higher order optimizers, then that problem can arise, especially if it is having boundary layers or interior layers.
No, but there are methods. Again, there are methods where you have the expansion term, some correction term, so you take care of the singularity.
Yeah.
I wrote several papers with Fanghai Zhang on that, and other people have. So you can use that, and then you take out the singular part, and then you're looking at the other part. So and then
but that is kind of assuming that where the layer is, where the location of the singularity is, that we already know roughly.
Well, it's at t equals 0.
But if it is having some sort of boundary layer or interior layer, then it is different. No.
Yeah, no, it's very easy because the residuals are picked there. Whenever you have singularity, the residuals are so large. So it's you have the residuals available, so you can see it. It's not so difficult numerically. But as I said, to judge the method, you wanted my feedback. So my feedback is to judge the method, you have to push it and compare it with a direct baseline.
Yeah, that is there. So you can definitely compare it to the ADM with P equal to 100. That is possible.
Well, I don't know if that's the best case because you need to sort of, it's a trade-off. It would be a trade-off. That's why it's a, how much you put in the prediction, how much in the correction. And you need to have a, it's kind of optimization problem.
Yes, of course, it is optimization. But
can you tell us, Arfad, when you, after you have this, let's say with p equals 1 and p equals 2, and you do have the ADM solution that is passed to the network, how many iterations on the network, how many epochs you need on for p equals 1 and for how many for p equals 2?
Yes, so sir, so if we use p is equal to 2, definitely we need more iteration than p is equal to 1, sir. Because I am stopping at the, so I am providing that maximum epoch is 2 lakh, but I am stopping the tolerance criteria up to e into 10 to the power minus 5. Yeah. So suppose n number of iteration is taking for p is equal to 1 to stop the iteration to achieve the iteration to achieve the tolerance up to e to the 1 into e to the power minus 5. And if I choose p is equal to 2, then to achieve the tolerance 1 into e to the power minus 5, it requires n plus n1 plus n2 epochs. That means for p is equal to 2, it requires more epochs than p is equal to 1, sir.
I see. I would think it would be the opposite, but that's fine. Okay, maybe I will read the paper carefully now. You have the preprint, right?
Yes.
Yes.
Yeah. Okay. Maybe somebody else will have questions. Sorry, monopolize.
Yeah.
Do we have any further questions for Arihant?
No.
If not, we could thank both the speakers, Arihant and Dr. Datta, for presenting their work today. And I'd like to close this week's Crunch seminar and hope you all have a nice break. Nice weekend.
Yeah. And thank you very much. Thanks all the speakers. Bye-bye.
Thank you, George.